Okay, kids, just real quickly here, I want to make this kind of brief, but I noticed just looking over lecture notes that there was a few kind of common misconceptions, and I tried to give some feedback to it on your notes, but I thought maybe this would be a way to where if you wanted to go back and address it before we wrap up the unit, you can just double check to make sure you're good or if there was any uncertainty. Long story short, I'd rather you have this and not need it than need it and not have it. So here's where we're at, right? You should be at a spot where if we're talking about a solid or a liquid or a gas, that you understand that that's a phase of matter, or if we say a state of matter, that means something, right? And when we talk about volume, which is the space that something occupies, and shape is, well, shape, you should be good with like, well, the solid is fixed, the shape is fixed. Liquids, the volume's fixed, but it's just going to take the shape of whatever container it is. It's not fixed, or it's not set, or it's not definite. And gas, nope, nope, not set, not set. In other words, they're just constantly moving all over the place, unless, of course, they're squished into a container as well. The attractive force. I didn't need an exact number here, right? I mean, this is just kind of a general way of thinking. Solids have lots, liquids have some, and it's not 100% accurate, but to get us through Chem A, I'm going to say that a gas has none. So that's where I was at with attractive force. And what I meant by that is, again, think back to that very first demo that I showed you with the little slingshot ammo, the little, brown clay balls with the glass dish where it was wiggling around. We saw that they were barely moving because they were all pretty well stuck together, kind of moving, and then really moving. So our particle speeds were just kind of like slow, faster, fastest. So, again, these aren't exact terms, they're general, but mentally, if you can kind of think of, there's a lot of stuff holding these together so they're not moving real fast, they're kind of vibrating in place. There's some force holding these together, but they can flow past each other, and there's really nothing holding these guys together, which, again, it's not 100% accurate, but they're really moving fast and far apart. That's good. So, volume, I want you to think of this as space, and mass, I want you to think of this as stuff. That should be pretty much more review than anything new. And there's technically more than 4 phases as well, but for Chem A, we're just going to talk about the 4 phases of matter, and then the 4th, we've just been calling plasma an ionized gas. And I haven't really gone into very much detail about what ionized means, but we've got a whole unit on that. So for now, think of this as like a very fast moving gas to where even electrons are actually free to leave. So on this part here, I wanted you to think of just the changes and what phase something started at and it ended at. So like if we're freezing, right? So if we're freezing, that means that you've got a liquid that becomes a solid. Or if we're melting, it's the opposite, right? We've got a solid that becomes a liquid. So notice how these guys here, solid to liquid, liquid to solid, they're basically going to be opposites. So for whether energy is absorbed or released, if you put like endo or exo here, that's fine. But I'm just going to abbreviate with either absorbed or released. If I got to get something to freeze, it's going to have to release energy or kick energy out. And then the particle changes, it's going to start to move slower. So why did it move slower? Well, because energy was kicked out. Or I guess another way of saying that was energy was released or kicked out, exothermic, and it started to move slower because it lost that energy. So the opposite here is to melt something, I got to get that substance to absorb energy and get those particles moving faster. These guys are kind of like opposites, right? For condensation, if something condensates, that's going to be where a gas becomes a liquid, and evaporation is the opposite. That's going to be where a liquid becomes a gas. So if I want fastest to slow down to just fast, it's going to have to release some energy. And if it's going to release some energy, it's going to slow down. If I want something to speed up or something sped up, it's because it absorbs some energy and it's going to start to move faster. So these are just supposed to be slowed down. Rather than putting another S for sped up, I just put slowed faster, slow, faster. These guys are kind of like the extreme ones. And let me do sublimation first, just because I get that, if you kind of think of these in chunks, sometimes it's a little bit easier. So I think of this as like, okay, well, if this is sublimation, it starts with an S. I'm starting with an S. Oh, it started from a solid. And that's that weird one where it jumps all the way up to a gas. And then deposition's got to be the opposite, where I go from a gas to a solid. So this was like where you have got frost, maybe on the grass. We're kind of moving into colder months now when this is being recorded. Sublimation, we're also moving towards like Halloween time, where if you've ever seen the dry ice, the frozen carbon dioxide, and it just gives off that like kind of plume for goes to a gas. Anyways, deposition, gas to solid, sublimation, solid to a gas. So if I want a gas to slow way down, it's going to have to release energy to slow down. If I want a solid to speed way up, well, it's going to have to absorb energy to speed up. These would be from ionization. Remember, a plasma is an ionized gas. So if a gas reaches ionization, that's a gas to a plasma that's absorbed energy to speed up. D usually is a prefix, deionization. Usually when something decreases, or D kind of means demoted, this would be like when a plasma goes down to a gas. So it must have released some energy to slow down. Okay, so what did I do here? My gas to my plasma, it absorbed. I think I put particle change here for S. I went sped up that time. I'm sorry. It should have been just F for faster. If I made any boo-boos in there, let me know and I'll go back and fix them. But basically, we should be kind of starting to get this. Looks like my sublimation from my solid to my gas. I made a little boo-boo there too, right? If I want a solid to be a gas and it absorbed energy, it should be faster. And if I want a gas to become a plasma, it should absorb energy to go fast. Sorry if I misspoke there and made a mistake. Let me know and I'll be happy to redo. So the next part here was looking at exo and endothermic. And remember, an exothermic reaction, that's going to be where heat is given off, or exo, exit. So if I touch something and it's giving off heat, or it's an exothermic reaction, it's going to be hot to the touch. Where endothermic, therm meaning heat, endothermic, that would be heat enters. So if I've got heat that enters, it'd feel cold to the touch. Why? Well, because it's yanking heat out of your hand, so it feels cold to the touch. So if you just put like exothermic is heat given off and endothermic is heat pulled in, or energy lost or energy pulled in or gained, I'm fine with that. But it's really more that you get the mental picture than you can remember the perfect definition. So hand warmers, these guys are going to be exo. I mean, obviously they're going to feel warm, right? So that would be giving off heat. An ice pack, it's going to be endo, because it's pulling in that heat and it's actually yanking heat from your hand. So if you've got questions about this, or maybe some that gave you some clarification, let me know. I'll be happy to go through this a little bit more detail. Here's something I want to just finish with real closely. Number 17, when I asked you about sweating, I had a lot of kids that thought, well, sweat is cooler than, there's you. Sweat's cooler than your body, and it's a hot day. Well, no, that's not actually what happens. Your body gets hot. There's a process that goes on that we'll go into more detail in class, but there's a process that goes on where when your body feels hot, you've got, basically sweat. We're just going to jump to that part of it. Or your body forces liquid water onto your skin. So if I got liquid water that's on my skin and that water evaporates off, say like maybe a breeze comes by and that water evaporates off. So if this is evaporation, ask yourself, what type of reaction is that? Well, if I've got liquid becoming a gas, right? So if I'm going from liquid to a gas, we said, well, liquid to a gas, that's going to require some energy to make this happen. Guess where it gets that energy from? Someone's going to say the sun, and I will throw a chair at you. It's not the sun. The energy that actually supplies this, or the heat that's supplied for this to occur, is your body. So as you put liquid water on your skin and this evaporation can take place, it's pulling heat off of your body, and that's going to cool you. Maybe you've been swimming on like a hot day, 90-degree type day, and you hop out of the pool or the lake or whatever, and a breeze comes by real quick and you like get the shivers. That's because even though it was real hot out and you were covered in all that water, all that evaporated off. It yanked a ton of energy out real quick, and you felt that little chill. Maybe you found that in the summertime on these real humid days, you don't feel like you're getting cooled off at all. Well, if there's a lot of water vapor maxing out the air here, or if we're going to say it's a real humid day, the air can't hold any more of this water vapor. It can't make any more gas or hold any more gas there. So what happens is you get that liquid water, that sweat on your skin, it can't really go anywhere because the air's maxed out. So you keep the heat, and then you got the sweat on you, and it's just when you feel kind of blah on those humid days. So it's kind of a simplified version, but I would like to go into more detail with it in class. But I just wanted to touch on it real quick. And if you've got specific questions, as always, please feel free to reach out to me. Until next time, toodaloo.